Okay, so last time we made our servers forget you on purpose. So now they are all identical and disposable. We can add one, kill one whenever we want. Which raises the obvious next question. Traffic is growing. One server is starting to drown. Requests piling up in a queue faster than it can finish them. So, do we make it a bigger box or do we add more boxes? And at high level, that is basically the whole of scaling. Two moves only. Scale up, take your one server and give it more power, a bigger box. Or scale out, keep the box the same and just add more of them, side by side. Both of them clear the queue. But each one breaks in its own way, and it is worth actually seeing how. Like, let us say you go to the more boxes route. You add 9 more servers. So, 10 in total. You would expect 10 times the traffic, right? And you measure it. And you not get 10 times, not even close. And figuring out where the rest of it went, that is the interesting part, honestly. So, bigger or more? And why does more not just multiply? Let's build it up properly. And it starts by not guessing. So first, what does scaling even mean? Because it is not make everything faster. Scaling just means the system can handle more users, more requests, while keeping things fast enough and not falling over. So, a scale system is not a faster system. It is one that stays standing as the load goes up. And to scale a server, you have to see it for what it actually is. At high level, a server is not a magic box. It is a bundle of budgets. So much CPU per second, so much memory, so much network, so many open connections. At low traffic, none of them is full. As traffic grows, one of them fills up first. And that one, the first thing to hit its limit, that is your bottleneck. That word just means the narrowest part, the thing that runs out first. Let's put a real number on it. Say each request needs about 8 milliseconds of CPU work, and we run one box with 4 CPUs and we keep it at 70%. You never want to run flat out. That works out to roughly 350 requests a second before it is full. Fine, until traffic climbs to say 1200 a second. Now, much more work is arriving than the box can finish. So the extra just waits. It stands in the line. And that queue, remember from the latency video, it is what makes everything feel slow. Not one slow request, a pile up. So here is the part beginners skip. Before you buy anything or add anything, do not guess what is full. Measure it. Look at the real numbers. CPU, memory, how long your database queries are taking, how deep the queue is, the error rate, and the P95 and P99, the slow and latencies. Because if the wall is your CPU and you go and add more memory, you just spend money and fix nothing, right? Find the bottleneck first, then we talk about how to move it. Okay, so the CPU is the bottleneck, the simplest move in the world. Give it more CPU. Take the 4 CPU box, make it a 16 CPU box. Now that is vertical scaling. People say scale up, one server, more power. And honestly, it is often the right first move. There is nothing to redesign, no extra machines, no splitting traffic. You just pick a bigger size and the queue clears. For a small or medium app, a lot of the time, that is all you need. And sometimes it is the only move. Let's say your work cannot be split, like a process that needs the whole dataset in memory at once. One big in memory database, you cannot cut that in half across two machines. So you need one machine big enough to hold the whole thing. Bigger box, no choice. But bigger has a ceiling. Even in the cloud, you cannot just keep clicking bigger forever. Even the biggest single box a cloud like AWS will rent you tops out somewhere around 2000 CPUs and 32 TB of memory, which sounds basically infinite. But that is the top of the menu. There is no bigger one to buy. And honestly, these top end boxes get expensive in a lopsided way. So, most apps hit the cost wall long before the size zone. But here is the real problem with one big box. It is one box. So when it dies, and machines do die, everything is down. There is no second box sitting there to catch the traffic. One big box is one big single point of failure. And even a normal upgrade usually needs a restart. So the box goes offline while it resizes. So the simple move quietly has a downtime cost built into it. So vertical is simple and sometimes the only way. But it is a dead end you can hit. And it is a single thing that can take your whole site down with it. So naturally, what about the other move? Okay, so the other move. Instead of one bigger box, keep the box the same and just add more of them. So, four small servers instead of one big one with the load balancer out front. That box that spreads the incoming requests across all of them. This is horizontal scaling. Scale out. And this one does not hit the same single box wall. You can just keep adding boxes for a long way though. Hold that thought, the system will still find a new wall later. We will get into it. And you get some genuinely nice things out of this. One server dies as long as there is spare capacity. The load balancer just routes around it, and the users may not even notice. You want to ship new code, you update the boxes one at a time. So the whole service never goes down all at once. Traffic spikes, you add boxes, it drops, you remove them. This is the shape a lot of the big systems actually run on. But, and this is exactly why last video mattered, the rule is more boxes only helps if any box can serve any request. If a user's login is stuck inside server's A memory, then more boxes just means more places for them to get logged out. So the servers have to be stateless. They hold nothing about you between requests. We moved that out to a shared store. That is the thing that makes add more boxes work at all. And something has to actually spread the requests across them. That is the load balancer. And it is clever enough to get its own video next time. So, scale out sounds like the clear winner, right? Keep adding boxes, route around failures, deploy without taking everything down. But there is a catch hiding inside, just add more. And it is the thing beginners usually miss. Okay, so back to the teaser. You add 9 more servers, 10 total, 10 times the traffic, right? And you measure it, and you got maybe 2 to 3 times. How much exactly depends on the setup, but it is nowhere near 10. So, where did all the rest of it go? Here is the first reason. Those 10 app servers are not really independent. They all still talk to the same database sitting behind them. So you did not remove the bottleneck, you just moved it. The wall used to be the app server CPU. Now, the wall is the one database that all of them are sharing. So, now all 10 servers are leaning on that one database and it hits its own limit even faster. And the second reason, the part you cannot split ends up capping the whole thing. Think about it. If even a small slice of every request has to go through one shared spot, like that one database or one lock, then no matter how many boxes you add, everyone still lines up for that one spot. So that shared piece itself sets your real limit, not the number of servers. That is the whole idea. Oh, and one more. Because people genuinely try this. More boxes does not fix slow code. If a request is slowing because your database query is missing an index, then 10 servers just run that same query 10 times over. You did not fix it, you multiplied it. So, fix the code first, then scale. So the honest picture is scaling is never really done. You scale the app servers and the database becomes the new bottleneck. And the database is harder to scale. You can add copies for reading, but every write still goes to the main copy. Splitting the writes across machines is a whole topic of its own called sharding for another day. The point for right now, the bottleneck always moves. You are never really scaling the system. You are chasing the next bottleneck only. And that is the real reframe of this whole thing. Every fix just relocates the problem. You find the bottleneck, you move it, and it shows up somewhere else. Okay, so putting it all together, what do you actually do? First, measure. Find the one resource that is full. Then, if it is a smallish app, a bigger box is often the simplest first move. Do not go and build a fleet you do not need yet. But, one caveat, if the thing has to stay up no matter what, you probably want more than one box from the day one anyway. Just so a single failure is not your whole site going down. And past a certain size, you go wide, more boxes. And honestly, real systems do both a sensible box size and several of them. And careful, more boxes is not automatic safety. If they all share one database or you push one bad deploy to all of them at once, they still go down together. Redundancy only helps when things can fail independently, right? Now, the nice payoff of scaling out is autoscaling, the system that watches the load and adds or removes boxes for you automatically. But it is not magic, it is a loop with a lag. It measures, it decides, it launches a new box, it waits for the box to warm up, and then it sends its traffic. And that warm up can be tens of seconds, sometimes minutes. So, a sudden spike can still hurt you while the new boxes are booting. That is why you keep a bit of headroom spare. So, step back. The question was never really bigger box or more boxes. It is where is the one thing that is full and can you split its work? That is the whole game, right? And every time you fix it, the bottleneck just moves somewhere else to the database, to a lock, to the network. So, you never done scaling. You are always finding the next bottleneck and moving it. Find it, feed it, or split it, and watch it move. So that is the real shift. Scaling was never about making things fast. It is about keeping the system standing as the load grows, bigger or more. It is just the how. The actual skill is knowing what is full and what breaks next. And that piece out front, quietly spreading the load, the one that makes more boxes actually work, that is the load balancer. And it is a lot more clever than it looks. That is next. See you there.